Hey physicists, sorry I couldn't be here with you today. Show must go on. So we are bouncing to 5-9 magnetic fields and the right-hand rule. Before we do that, maybe try this out as a little warm-up. It's topic 1, uncertainty. Stone falls down a certain well with a distance that we know, and we're going to use a kinematic equation and find the time. If you used this, you'd put in 20 for the d, you'd multiply by 0.5, you'd multiply by 2 to get rid of the 0.5, you'd divide by 10, you'd take the square root, and you get 2, so that makes sense. They're saying this is plus or minus 2 seconds is our uncertainty of the time, and we want to know the absolute uncertainty of the distance d based on that. So yeah, we're saying the uncertainty in the acceleration due to gravity is negligible. See if you can work through that and find the absolute uncertainty of the distance. Like how uncertain are we? Not the percentage, but the actual number. Just of the well. Just so you have a target, plus or minus 4 meters is what I got. Give that a shot. If you're not confident in that, maybe we can do it when I see you next. Cool, so pause and give it a shot. All right, so I hope you walked through this and got the plus or minus 4. I can show you how to do that if you're not sure next time I see you, but we're moving on to the magnetic fields and the right-hand rule or left-hand rule, depending on which way you look at it. And so here's some notes. We looked at an electric field being a region in space that exerts a force on certain objects with certain property. In that case, it was charge. And the magnetic field does the same thing. It exerts a force on a moving object with charge. Ultimately, a magnetic field and an electric field are the same thing. Sometimes they denote a magnetic field with a B field, and so those kind of go synonymously. They're very similar, and in fact they're the same thing, but magnetic fields deal with moving charges specifically, and those poles are called dipoles, and you see them in magnets. You see them in the magnetic field of the Earth. Magnetic field lines show which way the north pole of a magnet would turn, and so if a magnet was if you put it in space there, and this was the north, the magnet would turn to aim for this area. This is the north pole of a magnet. So it's attracted, I'm sure you're used to, it's attracted to the south magnetic pole of the Earth, which is located in the geographic North Pole. We call it the North Pole because north poles of magnets point to it. But because the north poles of magnets point to it, it's got to be a south magnetic pole. So actually, the South Pole is north. Messed up, right? Same with electric fields. The density of the field line, sometimes they call it the flux density, is a region where there's more lines. So if you looked right here, you can see more lines coming in and out than the same area. If we took that same circle, here there's 1, 2, 3 lines. Here's there's 1, 2, 3, 4, 5, 6, 12 lines. So this is 4 times as strong. The magnetic, the density of the field lines shows that it's stronger here than out here, which makes sense. It's stronger closer to the Earth than outside of the Earth. Cool. You could also see this if you took a bunch of little magnets and put them around a bar magnet. They would turn to orient towards the north. So like all of these are the norths. Maybe I can do them in red. So all of these are the north poles of these tiny magnets pointing towards the south magnetic pole of the bar magnet, which is kind of cool. All right. You can also get the same thing happening if you take two. This is not very useful because the magnetic field is just kind of spread all over. Looks kind of like this. But if you take 2 solid bar magnets, really flat ones, you put them next to each other, the north, a compass needle would point this way, right? with the north part being drawn towards the south magnetic pole of this one, and vice versa. And so this is actually a useful space with an even magnetic field. So we can do a lot of things with them. They're called uniform fields, and they're actually useful, where this is not that useful, or maybe not as useful. So I wanted to do this demo with you in class, but that's okay. I'll show you a little video of it. But a magnetic field is caused by currents. So like if you hooked up a battery, this is looking down on a battery, and this is a wire, an alligator clip, the electrons are flowing through it and moving like that way. Moving through. That current moving causes a magnetic field, right? That's a big thing that I want you to take away. Magnetic fields are caused by moving charges. And you could see that in something like this. If you turn no current on, these compasses are all lined up with the Earth's magnetic field. But if you turn the current on, they are overwhelmed by the magnetic field of the Earth is overwhelmed by the magnetic field coming through this current carrying wire, and you can see that they all turn and follow this pattern where they sort of revolve around this current carrying wire, and you can see which way the magnetic field is oriented based on this right hand rule. So you take your right hand. Is that your right hand or left hand? It's my right hand. I know I'm backwards on the video. You wrap it around the current carrying wire with your thumb in the direction of the current, and your fingers show which way the magnetic field is orbiting, and so which way the norths will point, essentially. So on this one, it makes sense when I'm looking at this diagram. If you think about your thumb in the direction of the current and wrap your fingers around it, my fingers are curling this way, right? My hand is like, my fingers are like that, and this is the palm of my hand, right? And my thumb is pointed up like that. Sorry. Here's a little video of that happening, which is kind of cool. Oh, come over. So if you, this is the wire, they're showing this magnet is oriented not at all with the wire, and then when they we'll clip this other lead in, so they're showing that there's no connection between the wire and the magnetic field, and once you clip that in, you can see that the wire influences the magnet in the compass, and eventually, if they hook it in there permanently, you know, it creates a field and makes a force on this. All right. So that's good. So we want to be able to we can use electricity to make motion, and that's the beginnings of motors, of electric motors, or motion at all. So another thing we can do with this, instead of just having a straight wire that I'll get my face back here. Instead of having a straight wire that we see some motion around, if you curled that wire into a loop, you get the beginnings of what they call a solenoid. So you can see this right hand rule applying here and here and here if you grab it differently on the way around. And so you get this floating and differentiating magnetic field. And overall, you can see all of these have the magnetic field. Let's see, if you grab the wire, my thumb's going in the direction of this. But as you're holding the loop of wire with the electrons walking through it, wow, electrons are doing this. Your hand is oriented differently, but you can see that the magnetic field is always coming out of the loop. It's pointing out. So like it comes in through here, and then right here it's pointing out of the loop. Same thing here, it comes in here, and right at the bottom it points out of the loop before it starts spinning around. And overall you get this flow of a magnetic field that's kind of pointing out. And once you have enough loops, you see that this magnetic field comes out like that. And this is exactly what we saw in a bar magnet, right? When we had this, oh, I deleted it with this, a bar magnet, right? We had this flow out and around like that in many spots. And what's cool about that is we can make out of metal, and sometimes they occur naturally on Earth, magnetite. But what's neat about this is with some loops of wire and a battery, we can make our own magnetism, which is useful, which is neat, as long as we run the current in the loop. And that's the basis of what they call a solenoid. Oh, come back. I didn't mean what I said. Right, so if we grab this wire, you can see the magnetic field spinning, and if we make that into several loops of wire, we can get our own magnet to occur. And so this is a little animation of what's happening in that solenoid that I kind of like. So you can see that here's the battery. They show you a little setup. They turn the power on, electrons flow, and you make a magnet. It affects the magnet. Pole detector is just a little magnet that can spin on its own axes. And so this is the solenoid. When you induce current, it makes a magnetic field that you can do something with, and we'll show you about like what you can do with that, which is kind of cool. Same thing here. If you put something in that, you can get, so like that's a neat trick, right? You get a magnetic field. But what's cool, if you put something magnetic, a ferromagnetic material, it doesn't even have to be a magnet in there. It's just metal. It's just ferromagnetic. It's iron. You can get it to move, right? So you can get it to pull in, or if you get a magnet, you'd even have some stronger interaction, and so you can get this to move or move out depending on which way you run the current, which is a useful trick. This is the idea behind a railgun, if you're into that sort of thing. What's also cool about this is, well, so you use this, you hear about the word solenoids in your car. So your car needs to start, which means it needs a little motor to help the big motor turn over. But you don't want the little motor engaged all the time, or else the big motor would spin it and break it. And so this piece up here is called the solenoid, and this is the magnetic coil, and it pulls this magnetic bar in and out and engages the electric starter motor. This is connected to your battery, and this is what cranks when you hear that. This cranks the big flywheel, and this flywheel is attached to your gasoline engine or your diesel engine. And this is the electric moving piece that is interacting. There's a magnetic field in here, and it moves this bar back and forth and engages this gear with the flywheel of your car. You don't want to always engaged, or else you end up having your car drive this little electric motor, which is bad. So anyway, we use these a lot, and they're really neat little inventions where you're taking electricity and turning it into motion, or vice versa, taking motion and turning it into electrical energy. We can talk about which way these the force on the little electric charges are pointed based on the magnetic field, and we have a fancy equation that discusses how much force is felt by a wire. So you want to be able to move things around with electricity. So we want to figure out how much force is going to be acting on things. So the B is the magnetic field, the current is how much current, and the length is the length of wire. The way we decide which way, or can tell which way the force is going to act, is with this left-hand rule, right? And so if you have current in a wire, here's our wire running this way, like that. Left-hand rule is using electrons, right? When sometimes you hear about people talking about right-hand rule, and that uses conventional current. So this, with left-hand rule, we're talking about direction of electron motion. So this is the way the electrons are marching. Use your left hand, that's your middle finger, this finger. Your index finger is talking about which way the field is pointing, and the thumb shows you which way the force is. So you can see people start flashing these physics gang signs when they're looking at which way the force is going to go. This is denoted like this, the magnetic field. If they're talking about it going into the page, they put X's, which you can kind of think of like an arrow flying away from you. You'd see the X of its little fins, stabilizing fins, and if you saw if the magnetic field was coming out at you, they put a point as if it were the point of the arrow. So that's a way to visualize what's going on where. Right. So this is they call this the left-hand, right-hand rule. It's left-handed rule if you're talking about the electron current, and it's right-handed rule if you're talking about the conventional current. Either way, it'll give you the same direction, right? I think the IBSL really just likes to use the left-hand rule to just keep it consistent. The flux density, the B, is measured in Tesla, and a Tesla causes 1 meter of wire carrying 1 amp of current to experience 1 Newton of force. So that's just kind of what that means. All right, and then this is the idea of an amp, right? So an amp talks about how much flow. We usually talk about the amperage of how much flow, but to be very specific, they've defined this as the force between 2 parallel conductors. So if you have like 2 wires, they say 1 amp causes this many newtons per meter that are 1 meter long. Right? And so, like, that's a little arbitrary, and it's a little too deep for us to get into why they chose this. But I know we talk about amperage as the amps is like the flow, but current is also, to be more specific, they talk about it as the force that they feel, because we can measure that a little more accurately than we can actual numbers of electrons flowing. Cool. All right. Well, I hope that gives you at least a kickstart. Try these 37, 38, 39, and I will see you next time we meet. Okay, bye. Oh, too much.